If you look at an oxygen atom sitting right in the middle of a molecule, the chemical groups surrounding it completely dictate its identity. By changing the neighborhood, we get 3 entirely different classes of compounds. Take an aliphatic, straight carbon chain and connect it directly to a hydroxyl group, an OH. That gives you an alcohol, like ethanol. But if we replace that straight chain with an aromatic benzene ring, the rules change. When the OH group is directly attached to the ring, we have a phenol. Then we can break that OH bond entirely. By trapping the oxygen atom between 2 separate carbon chains, we create an ether. The molecular neighborhood defines the chemical function. To understand how these molecules will react, we classify them by looking closely at the specific carbon atom bonded to the hydroxyl group. We simply count how many distinct carbon chains are connected to that central carbon. Depending on whether there are 1, 2, or 3 adjacent connections, we classify them as primary, secondary, or tertiary alcohols. If the molecule contains a double bond or an aromatic ring, we check for a buffer. Allylic and benzylic alcohols have an sp3 hybridized carbon sitting right between the OH group and the double bond or ring. Ethers follow a similar logic, but focus on symmetry. If the carbon chains flanking the oxygen match, it's symmetrical. If they don't, it's an unsymmetrical ether. Correctly identifying the neighboring carbon's hybridization and its surrounding connections is the required first step before predicting any chemical reactivity. Let's look at how we build these molecules. The first high-yield preparation pathway forms alcohols by reacting an alkene with water and an acid catalyst. The addition follows Markovnikov's rule, placing the OH group on the more substituted carbon. The second pathway is the reduction of carbonyls. The rule here is strict. Aldehydes consistently reduce to primary alcohols, while ketones always yield secondary alcohols. Let's apply that rule. If you apply a reducing agent to butanol, a 4-carbon aldehyde, what specific product do you get? Since it's an aldehyde, it yields the primary alcohol, butan-1-ol. Synthesizing phenols requires breaking tough aromatic bonds. In industry, we force chlorobenzene to convert into phenol by fusing it with sodium hydroxide under extreme temperature, around 623 Kelvin, and massive atmospheric pressure. Alcohols have exceptionally high boiling points compared to alkanes of similar mass. This happens because the hydrogen of one alcohol molecule interacts tightly with the oxygen of another, creating a strong intermolecular network called hydrogen bonding. This graph charts how boiling point shifts as the molecule grows. As the carbon chain elongates, the molecule's overall surface area increases. More surface area means stronger van der Waals forces, requiring more heat energy to boil. But look what happens when we rearrange those atoms into branches. Increased branching causes the molecule to become more compact and spherical. This decreases the available surface area, reducing the intermolecular forces and dropping the boiling point. A molecule's macro-level physical traits, including its exact boiling point and its ability to dissolve in water, are directly controlled by its micro-level geometry and its capacity for hydrogen bonding. For exams, phenol chemistry centers on 2 highly specific named reactions that branch off from a single starting point. Let's map these diverging paths. On the left, we have Kolbe's reaction. By exposing phenol to an alkaline medium and carbon dioxide, we convert it into salicylic acid. On the right is the Reimer-Tiemann reaction. Here, reacting phenol with chloroform and aqueous sodium hydroxide attaches an aldehyde group right at the ortho position, creating salicylaldehyde. Both of these pathways rely on the same chemical engine. The alkaline conditions generate a highly reactive intermediate state, the phenoxide ion, which actively drives these substitutions forward. Let's consolidate the core behaviors of our trio. Alcohols dominate physical properties through strong hydrogen bonding. Phenols utilize the aromatic ring for resonance-driven reactions. Ethers, lacking that reactive OH bond, remain mostly unreactive unless exposed to strong acids. This leads directly to the most frequently tested conceptual question: why are phenols significantly more acidic than regular alcohols? The answer lies in stability. When a phenol loses its proton, it forms a phenoxide ion. The aromatic ring allows the molecule to dynamically delocalize that negative charge through resonance. This stable resulting ion makes the molecule highly acidic. Mastering organic chemistry doesn't require rote memorization of endless equations. You just need to understand the localized rules created by the oxygen atom's environment.